All right, so this is 3-1, solving systems using tables and graph, and thank goodness our learning objective is to solve a linear system using a table or graph. So if we're going to solve a system of equations, we need to know what that is. So I'm going to be referencing the term system of equations, and it is a set of two or more equations. So a system of equations is just a set of two or more equations. So instead of one equation, we're going to have a couple or more. So our essential understanding, this part you do not have to write down. Everything else is a must write down. To solve a system of equations, find a set of values that replace the variables in the equations and make each equation true. So it is an x and a y value that make each equation, because we have two or more, true. Specifically, we're going to talk in this section about a linear system, to solve linear systems. What that means is specifically it's going to have linear equations, so y equals mx plus b type of equations. So when we're solving a linear system, we're going to have a line and another line, and we're going to find out which x and y value make both of those lines true. And in real people terms, it's where my two lines cross. Solving a linear system means finding where my two lines meet up. A solution of a system is a set of values for which the variable, a set of values for the variables that makes all the equations true. Set of values for the variables that make all the equations true. Similar to linear system, except it's the solution to it. All right, so let's apply this. I have two linear equations. I have x minus 2y equals 4 and 3x plus y equals 5. The first one I'm going to do is the table because I don't like the table. So let's get that one out of the way first. Okay, so we're going to set up an XY table. So if I have an XY table, it will be helpful if I have each of these equations solved for y. So I'm going to go ahead and do that. So I'm going to solve this equation for y. Because if I'm plugging in an x value, so first let's plug x. So this is negative x plus 4 over 2. And then for my other one, I'm going to subtract 3x from both sides. So y equals negative 3x plus 5. Okay, so step one, I solved each of these for y. Let me circle so that you guys can see them. The crazy way I'm writing down here. So now I'm just going to pick some x values, and they are going to be, I'm going to pick some positive ones and some negative ones, and I'm definitely going to include 0, so I'm going to start negative 2, negative 1, 0, 1, and 2. And hopefully my numbers come together. If they don't, I'm going to have to add on to my table to make sure that they eventually meet up. Okay, so for my first value here, I'm going to put negative 2 in for x. So minus a negative 2 is plus 2, so it's positive 2. Plus 4 is 6. 6 divided by 2 is 3. I'm going to put negative 1 minus a negative 1 is positive 1. Plus 4 is 5. 5 divided by 2 is 2.5. 0 plus 4 is 4. Divided by 2 is 2. 1, put the negative on it. Minus 1 plus 4 is 3. 3 divided by 2 is 1.5. Tell me you guys are seeing a pattern here. 2, negative 2 plus 4 is 2. 2 divided by 2 is 1. All right, now let's apply that to my other linear equation. Negative 3 times negative 2 is 6. 6 plus 5 is 11. So this is definitely not a solution because I want my y's to be with it. Negative 3 times negative 1 is 3 plus 5 is 8. Once again, 2.5 and 8, not the same. 0. Negative 3 times 0 is 0 plus 5 is 5. 1. Negative 3 times 1 is negative 3 plus 5 is 2. And then 2. Negative 3 times 2 is negative 6. And negative 6 plus 5 is negative 1. We're going to take a moment and I'm going to show you guys how to make a table in your graphing calculator or using your graphing utility online. Okay, so we see from our table that our solution happens somewhere between 1 and 2 because our numbers are kind of marching closer and closer together. We got 2 and 5, 1.5 and 2, and then suddenly they cross and start galloping away from each other, 1 and negative 1. So we're going to use the graph to kind of help us out here. Okay, so if I have my x and y axis, and I'm going to rewrite this equation just a little bit down here so that it looks like a normal equation. Let's go black. Okay, so I'm going to distribute. This is going to be negative 1/2 x plus 2. So I'm just distributing the divided by 2 to the negative x over 2 and to the 4. So now I can graph this at, it has an intercept at 2, and it has a slope of down 1 over 2. And to keep my graph as accurate as possible, I continue that pattern. Okay, so let's get Mr. Line. Straight line. And then this one, the purple line, we know is plus 5 is our intercept. And its slope is down 3 over 1. So we start 1, 2, 3, 4, 5. And we go down 3. Even when you graph this on a graphing utility, when you go to turn papers in, the paper has to have the right intercepts, the correct slope. Let me put my line down. Take them purple. Okay, so when we graph this, we see that our two lines intersect between 1 and 2 and actually closer to 1. The downside to using a table or using a graph is sometimes you won't get an accurate output. in this case, we have to guess that it's about, so our lines cross at about, like in this case, it's like 1.1 and 1.2 from the graph. And you have to be okay letting that go when it is one of those non-integer answers. We have to be okay using our best estimation. All right, let's look at this word problem and see how to use this process with data and put it together and get an answer out. Okay, so the diagram shows the birth lengths and growth rates of two species of sharks. And I wrote it. Sorry, it's blocking. I did it twice. Let's go ahead and delete this. If the growth rate stays the same, what age would a spiny dogfish and a Greenland shark be the same length? Go ahead and in your notes abbreviate this instruction. All right, so X is going to be the age of our shark and Y is going to be the length of our shark. And does it make sense that our shark's length is dependent upon our age of our shark? Yeah, because newborn baby shark not as big as a giant mama shark that's been living around 20 years. All right, so we're going to go Y equals whatever our rate is, that's the same as a slope. Anywhere you see slope or rate, put that in as your slope in your equation, plus whatever length our little shark starts out at, which is our y-intercept, our starting point, our starting length. And then our spiny dogfish shark, he is y equals, he is growing 1.5 centimeters per year, and he starts out at 22 centimeters. So we need to find, the question says, when should they be the same length? So this is the... Okay, so take a moment. Let's go both at, let's do increments. Actually, just do ones. Let's do the first, document the first 5 years of shark life for our two little sharks here. Okay, so if you plug in increments of 1 and look what happens between 1 through 5, we get that our numbers aren't increasing fast enough to actually meet up. They are both increasing, but just not fast enough. So then if at this point you don't want to put in a whole bunch of work, you don't want to continue counting by ones if your lines aren't matching up. So I started counting by 5s, and I saw that the next 2 increments of 5, or the next 3 increments of 5 showed us that our sharks at 20 years are both going to be 52 centimeters. So the answer to this question, so the solution is 20, 52.
I know. So cool.
So we're going to verify this by graphing. So if we go to our graphing utility, and we put in y equals 0.75x plus 37, and y equals 1.5x plus 22. Make sure we're looking at, so our green line here is one chart and our blue line here is the other. And you can see that they do meet up here at 20, 52. So if I was doing this in my graphing calculator, I would put this first equation in for y1, this second equation in for y2. I would go to my calculate, which is second in graph, and I would click on the intersect. Enter, 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 and it gives you the intersect on your graphing calculator. All right, so on your paper, you're going to draw a sketch of this graph. It should have the intersection point. Thank you.
It says when I.
So if we extend this out, if the growth rate continues, how long will each shark is 25 years old? So we just go to our table, continue it out, and I go 0.75 times 25 plus 37, 55.75, and 1.5 times 25 plus 22. 59.5. All right, so what if we have some more crazier data? So this table shows the population of San Diego and Detroit metropolitan regions. When were the population of these regions equal? What was that population? So we are going to use a graphing utility to help us calculate this data. So I'll give you a moment. For those of you guys who are on the computer, I'll give you a nice website that you can use to calculate this out. Okay, so we enter our X and Y values, our numbers only. I used the Alcula.com, calculator statistics. I entered my year and my population.
For the calculator, what do you do to enter it?
Click your submit data, and then write down the regression line equation. Okay, so after you enter the first set of data, you're going to get this regression line equation. What you're going to do then is, if you're on your graphing calculator in list 3, you're going to put in the other, I think it's Detroit data. I'm just going to go and change my second value to match the Detroit data.
So we don't even have to do list 3, we just change list 2.
You can, yeah, correct. If
But
you
can
don't.
we just still do list 3
And
keep list 2?
All right, when you enter in the second Detroit data, you get out a linear regression equation of 19,217.55x negative plus 39323626.9. So our intercept is the 39323626.9, and our slope is the negative 19,217.6. All right, so the last thing we're going to do is we're going to graph these two functions on our Desmos. So we go to Desmos and we get 17,816.59 x minus 3438 5468 2.
Is there an easy way to calculate this on the calculator? if you just
You have to enter the data.
really.
There's no way to avoid data entry. 393236 269 minus 192 175 0.5x. Okay, so if we put our decimal point in the right place. Now, if you're like me and you have your graph set here, you go, oh, I need to change my graph settings, and this is for your graphing calculator as well. So we know we are not looking at time less than 1950 because we have no record of time. So we're going to say 1940 is our y-axis. And we're not looking at any time larger than what? Probably 2100. And let's count by decades. So I definitely am going to go on my y-axis. If you look at our starting points, I got a pretty huge negative starting point. So I'm going to go, our population technically can't be negative, can't have negative humans, so we're going to keep our population positive. But I'm going to get it really big here. So this is like 400 million. So let's go. And let's count by, I don't know.
5 million? 50 million?
50 millions?
50 million?
Wait, what are you counting by with the X?
No. I was counting by tens, but now I'm zooming out because I'm trying to find where they cross.
Or window range. Okay, well.
Oh.
Check it out, calculator.
So I'm just trying to find out where these two lines cross. So I'm zooming.
Zoom. It's the monster.
Right here. Thank goodness. Okay, so make sure you include this information in your notes. Graphical solutions of linear systems. It's important you know that when you solve an equation, whether it's using a graph, a table, or algebra, that when you have one solution, this is a consistent system and it's independent system. When you have lines that are coinciding or they're one right on top, it's the same, ends up being the same line, one on top of the other. There are infinitely many solutions. It is a consistent system and it's a dependent system. And then when you have parallel lines, that means that two lines never cross, that it's no solution and it's inconsistent. So consistent, independent, consistent, dependent, and inconsistent. All right, let's see how we can, without graphing, determine if you're independent, dependent, or inconsistent. So the first thing I'm going to do for each of my equations is solve for y. I find it's easier when I'm solved for y to to compare my equations. So I'm going to take this equation here. I'm going to add 3x to both sides. And I get y equals 3x plus 4. And I'm going to take this equation here. I'm going to subtract x from both sides. I get negative 1/3 y equals negative x plus 1. I'm going to multiply everything by negative 3. because that is the reciprocal of negative 1/3. So then I get y equals 3x minus 3. So if I'm looking at A, my first equation is y equals 3x plus 4. My slope is 3. My y-intercept is 4. My second equation is y equals 3x minus 3. My slope is 3, and my y-intercept is negative 3. When your slopes are the same, your lines are parallel. If your lines are parallel, then you are inconsistent. Okay. Let's look at our next equation. And I'm going to subtract 2x. And I'm going to divide by 3. And I get y equals negative 2/3 x plus 1/3. And then for the second one, I'm going to subtract 4x from both sides. So I get y equals negative 4x minus 3. I compare my slopes. The slopes are not equal, and one equation is not a multiple of the other. They're not the same equation. So we say that these are lines that cross. So that's the situation here, and we are independent. And they don't ask, but we are also consistent. All right, last but not least, let's look at this equation here. This one is already solved for y, so yay! The next one, I subtract 6x from both sides. And divide by 3. Sorry, divide by negative 3. I get, for my second equation, I get y equals negative 6 divided by negative 3 is 2. And 9 divided by negative 3 is negative 2. So you look, compare the two equations, they are the same equation. 2x minus 3 equals y. That is the situation here. There are infinitely many solutions. And they're the same line, so we are dependent. And that's how you tell one solution, infinitely many solutions, or no solutions. Okay, take a moment and write your summary at the bottom of these notes and complete your practice. Thank you.